before getting into the concept of passing by reference and passing by value, let's talk about bits. I think this will be useful information for you. So everything in a computer is stored using ones or zeros, and each one of these can be called a bit. Now, how does it store information? So let's say you have just one bit to work with. How many different possibilities can this have? Either it can be a 0 or it can be a 1. So there are a total of 2 possibilities if you just have one bit to work with. Let's say you have 2 bits to work with. Then you will have 4 different possibilities because each one of them can be either a 0 or a 1. So at first it can be a 0 for the first bit and it can be a 0 for the second bit as well. Or the second bit is 1 and the first bit is 0. That's another possibility. Or the first bit is 1 and the second bit is 0. That is another possibility. And the last possibility is that both of them are 1. So there are 4 different values that you can store using 2 bits, no more. What if you have 3 bits? In that case, you'll have 8 different possibilities. So you can store 8 different values. What if you have 4 bits? For 4 bits, you can have 16 different possibilities, and you can store 16 different values. So our current computers and our current phones have really large memories. They're not in the order of bits, they're in the order of gigabytes. Now, 8 bits together make 1 byte, and there are a billion bytes in a gigabyte. More than a billion, actually. So that's a lot of things that you can store using all of those bits, right? Great. Now that we understand that, let's see how we retrieve information from bits. Now, think of a normal number, not a binary number. Think of an integer, let's say 356. Now, if you think, these can be bits as well, right? But just like here, we could only have 2 different bits. Here, we can have 10 different bits, right? Because we can store anything in one of these places from 0 to 9. And that's 10 different digits that we can use here, right? So that is why this is called base 10. And our everyday numbers that we use are base 10. However, the numbers that computers use are base 2. Because there are only 2 things that are possible in each bit. Here, 10 things are possible in each place, right? Here, only 2 things are possible in each bit, which is why we call it base 2. So how does base 10 help us get this number? What does this really mean? What this really means is this is the 0th position, this is the first position, and this is the second position. So what's really happening is that you're actually multiplying 3 with 10 to the 2 plus 5 with 10 to the 1 and 6 with 10 to the 0. So 3 multiplied by 10 squared gives you 300. 5 multiplied by 10 gives you 50. And 6 multiplied by 10 to the 0 gives you 6 because 10 to the 0 is equal to 1. Anything to the power 0 gives us 1. So this is how you get 356. And you can experiment like this with any number and see that this is exactly what you're doing. You are taking this place and raising that to the power of 10. And then you're multiplying whatever digit you have with that number. So what you're basically doing is that you're taking this number here, you're multiplying it with 10 to the power of the index. So let's think of another example. If we think of 5,634, what's happening here? It's the same thing. It's 5 into 10 to the 3, because this is the 3rd position, this is the 2nd position, this is the 1st, and this is the 0th position. 5 into 10 to the 3, 6 into 10 to the 2, 3 multiplied by 10 to the 1, and 4 multiplied by 10 to the 0. And this gives us 5,000, this gives us 600, this gives us 30, and this gives us 4. And that is how you actually get to the number 5,634. So let's do the same thing for base 2. Let's take any number in binary. So let's say we take 0, 1, 1, 1. Since this is base 2, we won't be having powers of 10. because this is base 2, we'll be having powers of 2. So in this case, 0 is multiplied by 2 cubed, and 1 is multiplied by 2 squared. 1 is again multiplied by 2 to the 1, and 1 is multiplied by 2 to the 0. So what this comes out to be is this is 0, this is 4, this is 2, and this is 1, which comes out to be 7. And basically, 0, 1, 1, 1 is the binary representation of the integer 7. And that's exactly what you see here. And if you do this for any of these numbers, you'll see that you'll find that the result is one of these numbers. So if we do 1, 1, 0, 0, this will come out to be 12. Let's see how that happens. So we'll have 1, 1, 0, 0. This is the third position, this is the second position, this is the first position, and this is the 0th position. So we'll do 1 multiplied by 2 cubed plus 1 multiplied by 2 squared plus 0 multiplied by 2, 1, and 0 multiplied by 2 to the 0. This gives us 8, this gives us 4, this gives us 0, and this gives us 0, which ultimately gives us 12, which is exactly what this binary number represents, 12. So that is how you can think of binary numbers storing information. So in the data type video, when we explained different data types, we said that there are 4 different types of integers. You have byte, you had short, you had int, and you had long, right? So let's just talk about int type. We'll talk about 32 bits. So let's say you define a variable named x and you say this will store 5. So what's happening is that in your memory, which is the RAM, exactly 32 bits are being allocated for x. So think of 32 bits. The rightmost bit becomes 1, then the bit to the left of that becomes 0, then the bit to the left of that becomes 1, the left of that becomes 0, and all of the other 24 bits are 0. And this represents 5. All those zeros, like 24 zeros and then 0101, is stored in this memory location. Exactly 32 bits. So you have the binary of 5 stored here. And this is the memory location that is accessed whenever you use x. Now let's say you create another variable y and you say y equals x. What's going to happen? Another memory location exactly 32 bits long would be allocated for y. And then every bit from x will be copied to y. So if this memory location had 0101 and then 24 other zeros, then exactly that will be copied to y. And it would be 0101 and there would be 24 other zeros before that because there are 32 bits, right? And all of them would be used. So 0000 and there are 24 zeros and then 0101. Exactly what was there in the memory location for x gets copied to the memory location for y. So now let's say the next statement that you write is x equals 6. So this was your first statement, and here you created a variable named x, which was of integer data type, and you stored 5 in it. After that, this became your next statement, where you created another variable named y, which was integer type, and you stored the value that was stored in x in y. So whatever was stored in x, you stored that in y. And then this third statement is where you just said x equals to 6. So now the value of x changes, which means that this value changes. The binary representation of 6 is 0110, right? So now all the first 24 bits do not need to be changed. They'll remain as 0. And then these bits will become 0110, right? So you see, when you change the value of x, the value of x in the memory changes and its binary representation is changed. However, that does not mean that the value of y has changed, right? Y has remained whatever you assigned to it before. You copied the value of x in y. So the new memory location for y was created and the value of x was then copied here. And so when you change x to a different number, y does not get affected. So this is an example of passing by value, and this only happens for primitive data types. So whenever you assign one primitive variable to another, we say that primitive data types are passed by value because the value completely gets copied to the new variable that you create. So this is an example of passing by value. Now let's say we're creating an object, or we're creating a non-primitive data type. You remember that arrays are non-primitive data type, right? So if we create a new integer array, let's say we say my array, and let's say we have 2, 3, 4, and 5 stored in this array, right? So this is what the array looks like. However, when we think of the variable my array, how is this represented in memory? How is this stored in memory? So in your memory, for these 4 different integers, a big memory location is allocated, whatever is needed for these 4 integers. And 2, 3, 4, and 5 are stored there in binary, of course. But when we are trying to access my array, what are we accessing? Are we accessing this memory directly? Remember that when we had int x equals 5, for this, a 32-bit memory was allocated, and x directly referred to this memory where 5 was stored, right, in binary. But what happens for my array? My array is a non-primitive type. This is a primitive type. So what happens for my array is that a 32-bit memory location is allocated, and this memory location does not store the array. This is where my array points to. But this memory location does not store the array. Remember that every memory location has an address. And if you look at that address in Java, it looks something like this. Some text like this. So this is basically the memory location address. This part where the array is stored, this big memory location, this has some address, right? And it'll be something like this. That address is stored here. The array is not stored here. So my array refers to the address, and my array does not refer to this memory location directly. Now, this address is the address of this memory location. This memory location is the same address as the one stored here. So this memory location's address is this, and this address is stored in a 32-bit memory here. And this is what my array refers to. This would happen with any non-primitive type. So if you create an object, let's say we created the dog object, remember, named Sherlock. When you create the Sherlock object, that Sherlock object will be stored in some big memory location where all the different attributes and methods of Sherlock are stored. However, this variable, Sherlock, does not directly point to this memory location. This variable, Sherlock, points to a memory location here somewhere, all right? And this is only 32 bits. So now let's say the address of this whole memory location is something like that, right? So let's say this is the address of this big memory location. This address would be stored here. And Sherlock is in this statement, right? So we might have had dog equals new dog and then the constructor, right? So this would not refer to this new object, even though we created a new object and we assigned it to Sherlock. That does not mean that Sherlock points to the memory location where the object is stored. It means that Sherlock is basically pointing to this 32-bit memory location. And in this 32-bit memory location, the address of the object is stored. So now, let's say you create another dog, right? You create another dog named Molster. And let's say here, you just do not want to create a new object using this constructor. You just want to copy whatever Sherlock has, right? You just say that the new Molster dog is just a copy of Sherlock. That's what you want to say. Now, Sherlock points to this memory location where a memory address is stored. And this memory address then points to the object, right? So when you say this, dog Molster equals Sherlock, this whole object does not get copied. A new copy of the object does not get created. Only the address that's stored here gets passed to this new variable. So you might have another 32-bit memory location that gets assigned for Molster, and the same address that was in Sherlock gets copied. And what does this address point to? This address points to the same object. So basically, you did not create a copy of the object. You just created another variable that points to the same object. So remember when we had integer x and then we had integer y equals x and then we changed x equals 6. So when we changed x, y did not change, right? That's what we showed just a little bit ago, right? But for this, the whole story is different. Because they point to the same object, if you change the object Sherlock in any way, Molster also gets changed. Because basically they're pointing to the same object. If you change Sherlock, something gets changed here. Now when you're talking to Molster, Molster is pointing to the same object and it will see the same changes. So if Sherlock has any changes, Molster also feels those changes. But here, if x is changed, y does not get changed. This was passing by value. The whole value was being copied to y. This is passing by reference. This address is actually a reference to the memory location where the object actually is, right? So this is called passing by reference. So remember that primitive types are passed by value and all non-primitive types are passed by reference. And reference means the address.